Let's talk differentiability. That word right there, differentiability. If I were able to try to describe what that means in my broken grammar, because I math, differentiability is the ability to take the derivative. The ability to take the derivative. What that's really saying is, can I take the derivative at this point, or can I take the derivative of this function? Okay? One thing that we're already familiar with is continuity. If a function is continuous, we talked about that. Here are 3 examples where our function was not continuous. We have a removable discontinuity, which is our whole, because we could fill it in, right? Here we have a jump discontinuity, because our function has that literal jump, and our asymptote. At each one of these discontinuities, those functions are not differentiable at that point. If I have a hole in the graph, do I have a slope where there's a hole? If the graph itself doesn't exist, how can there be a slope, right? Same thing here. If I wanted to find the slope at that point, well, you have 2 points. What are you doing? Similar to limits, if the left side and the right side don't match, the limit doesn't exist. Well, by definition, a derivative is a limit as h approaches 0. So if the slopes don't match, those are different looking slopes, and there's a discontinuity, there's no slope at that point. And the same thing when we have an asymptote. If there's an asymptote, there's no slope, because there's no function at that point. Okay? So, if there's a discontinuity, you cannot take the derivative at that point. Over here, this piece, I can find the derivative of those points. Those are fine. The issue is at the discontinuity. Okay? So discontinuity, no differentiability. But we also have issues when the function is continuous. Okay? And those look like this. So when we have continuity, we still have differentiability issues. The first one, I'm going to use the example of the absolute value of x. That graph looks like this. So we have an issue here where those 2 lines meet. With our absolute value, we get that v. Okay, so we're meeting at this point. Like I just mentioned earlier, derivatives are limits. The limit is h approaches 0. If the right side limit and the left side limit don't match, then the limit doesn't exist. So that's what's happening here at this point, the corner. I have a negative slope on this side and a positive slope on this side. So what's the slope at that point? Because the left side and the right side are different, the slope at that point doesn't exist. It's not differentiable. The issue here, we refer to this, real scientific name here, we call it a corner. I can't take the derivative at any corner on a function. Similar, if I look at x to the 2/3, that looks like this. We run into the same issue. Our left side and our right side, they have different slopes. So at that point, because my slopes are different, the derivative at that point doesn't exist. So again, we have that issue at our point here. We call this one a cusp. So it's not a straight line like a corner. It's kind of got these bendies. So we're just going to call that a cusp. The function's continuous, but it's not differentiable because of those 2 different slopes meeting at one point. And our last example I'm going to use is the cube root of x. And that graph looks something like this. Rough sketch, but we get the same idea. My issue comes in right here. What's happening with our square root of x graph is at this point, our our tangent is vertical, okay? And vertical lines, they don't have a defined slope. The slope is literally undefined. So because of this vertical tangent, we have an issue. Again, vertical lines, they have an undefined slope. Slope is derivative, so if the slope is undefined, the derivative is undefined. Make sense, right? So even though these are 3 examples of continuous graphs, if it's continuous, we can take the derivative. There's no discontinuities, no issues, except these 3 issues: corners, cusps, and vertical tangents. At those points, the derivatives don't exist. It's not differentiable at those points. So something I really want you to remember, this is going in your gee whiz, you're going to keep it in the top of your brain at all times. Differentiability, meaning if I am able to take the derivative of a function at every single point. Differentiability guarantees continuity. So if you can take the derivative, you are guaranteed that that function is continuous. There's no holes, there's no jumps, there's no asymptotes. If you can take the derivative, the function is continuous. But it doesn't work the other way, okay? Continuity does not guarantee differentiability. Okay? Just because a function is continuous does not mean you have a derivative at every point. Here are 3 examples. Okay? So remember, differentiability guarantees continuity. We're going to use that in the future.